So welcome to the next lecture on signals and systems, where we continue our discussion of discrete time systems, right? Just to recapitulate from the previous lecture, we had established what we mean by a discrete time or a discrete independent variable, right? Basically, we said that an independent variable is discrete if it can be put in one-to-one correspondence with a set of integers in some way. It is not necessary. For example, the variable could be two-dimensional. It could be two-dimensional space that has been discretized. Okay, it could be time that has been discretized. It could be a combination of time and space that has been discretized. The discretization could be uniform or non-uniform. However, we had dealt with the case of systems where both the input and the output variables, I mean both the input and the output signals had independent variables that were discretized, right? Now, we had also established the properties that were pertinent to the context of continuous time systems in the context of discrete time systems. To recall, we had talked about the property of memory, we had talked about the property of causality, of shift invariance, and of stability. And finally, we had discussed the property of linearity, which had two parts, additivity and homogeneity. Now, today we take further the study of discrete time systems that are linear and shift invariant, all right? Well, the ideas were very similar to what we had for the case of continuous time systems. In fact, they are much easier in the context of discrete time systems because one can define the impulse so much more neatly in the context of discrete time system. It's a well-defined sequence. Unlike the continuous time case where the impulse is not really a function, it's a generalized function or a mathematical object which can only be characterized under an integral sign, right? So taking further from there, let's look at the unit impulse sequence once again. The unit impulse sequence is defined by delta n given by 1 for n equal to 0 and 0 else. And we noted that any sequence xn can be written as a sum. Well, we write xn as a sum or a weighted sum of impulses. The impulse located at n equal to k is delta n minus k. And this impulse is weighted by the value of the sequence at k. So, a summation on xk delta n minus k gives us the original sequence, right? Now, the same argument that we had for the context of continuous time systems can be carried forth to discrete time. Namely, if I know the response to delta n, it should be possible for me to find the response to an arbitrary xn by using the property of linearity and shift invariance. Let's go step by step. So, suppose we knew that when delta n is input to the system, the output sequence is hn. Now, please note, here we need to talk about input sequence and output sequence. I am re-emphasizing that from the previous lecture. Now, here, suppose the system is shift invariant, right? So, shift invariance tells us that if delta n minus k is applied to the discrete time system, well, I should really avoid saying discrete time system actually. because this applies to any discrete system, right, where the independent variables are discrete. The output shall also be shifted by the same k, right? So it would give you h of n minus k. Now, the next step is that of homogeneity. So, because the system is homogeneous or it obeys scaling, when we multiply the input here by x of k is like a constant. So, when we multiply this by x of k, the output is also multiplied by the same xk. All right? And finally, we use the property of additivity. In fact, I will write it right here. Because of additivity, if I sum this over k, the output is also summed over k. So, homogeneity gives us this part and additivity gives us this part. Right? So, needless to say, now this is x of n. This is the input x of n. And this must therefore be the output y of n. Right? That must be the output y of n. And clearly, the input x of n, the impulse response h of n, and the output y of n are related through the same or a similar kind of operation in discrete time which we had in continuous time, namely that of convolution. So, this expression that we have here expresses or illustrates an operation between two sequences as opposed to between two numbers once again. This is an operation between two sequences, I must emphasize that. By that what I mean is that for every point yn, there is a different operation being performed there, which in principle involves all the points of the input and output sequences. Right? So, in reality, for every point on the output, we can potentially involve the whole of the sequence xn and the whole of the sequence yn. It is of course true that in a lot of for a lot of points yn, only a selected set of the points xn and hn might really collide in the convolution. But in principle, we should remember that it is the whole sequence xn, all the points of xn and all the points of hn which produce every point of yn. And that is why we say it is an operation between two sequences, not between two numbers. Yeah? Now, we must illustrate the idea of convolution in discrete time with examples. So, let us take for example the convolution of an exponential sequence as we did with the unit step sequence. So, an example of convolution. Let us convolve the sequence xn equal to, let us say half raised to the power of n un. Now, recall that un is a unit step sequence defined by un is equal to 1 for n greater than or equal to 0 and 0 for n less than 0. called the unit step sequence. We wish to convolve this with the sequence Hn given by Un. Now again, it is up to us to choose which sequence to, fix and which sequence to move. Now, the ideas that we had developed for the case of continuous time convolution carry over to discrete time convolution. Let me just briefly review them so that we put things in perspective. So, here we are. These are the sequences that we wish to convolve. Let me write them down just on top here. Convolve with Un. Now, you see, for exactly the same reasons as in the context of continuous time, we can show that convolution is commutative in discrete time, right? So, this convolution is commutative. Discrete variables also. The arguments are exactly identical. I shall just quickly review the argument. The argument was that if you look at the summation xk hn minus k, then we can make the substitution of variable p is equal to n minus k. And then k becomes n minus p. And when k runs from minus infinity to plus infinity on the integer axis, p also runs from minus infinity to plus infinity on the integer axis for any fixed value of n. So the argument to show that convolution is commutative is exactly identical or very similar to the case of continuous time systems. So actually the point there is that we may choose, you see, just as in the continuous time case we had the notion of fixing one sequence and moving the other, the same notion carries over to discrete time or discrete variables. So if you look at the expression summation on k, xk hn minus k, here we are understanding the variable or rather the sequence h to be moved. We understand h to be moved and x to be fixed, right? How are we going to move the sequence h? We are going to put at the point k. So you see, visualize the situation here. Let's write down for this particular hn is equal to un. Let us write down the sequence hn minus k, right? Now for the same reasons as in the continuous variable case, we can show that whatever was at 0 shall be brought to n in hn minus k. So here at the point n we have 1, and whatever was beyond 0 in the original sequence in order must appear before n in order, in the reverse order, or backwards. Whatever was beyond n forwards, beyond 0 forwards in the original sequence must appear before n and reverse in hn minus k, right? So how does the sequence appear? At n you have 1, that's at 0, that's what was there at 0, and then in u of n you have zeros before n equal to 0 and ones after n equal to 0. So here you shall have ones before n and zeros after n. So you will have a string of ones like this. and zeros here. This is u of n minus k, which is equal to h of n minus k. Yeah. Now let's get a feel of the convolution by sketching the sequence x of k as well. This is h of n minus k. Let's sketch the sequence x of k as well. So x of k looks like this: 1 at 0, half at 1, 1/4 at 2, and so on, exponentially decaying. This is x of k. And our aim is to convolve these. I mean, what it really means is that we wish to, for every point n, we multiply these sequences now, point by point, as opposed to continuous time functions. So in the case of continuous functions, we multiplied the functions and found the area. Here what are we going to do? We are going to multiply the sequence xk and the sequence hn minus k. Both of these treated as sequences in k as opposed to n. These are now sequences in k, not in n. Right? So we multiply them point by point. Point by point means the corresponding point here will be multiplied by the corresponding point here. The point number 1 here will get multiplied by the point number 1 here, and so on. Right? That's what this says. Multiply the corresponding points k and then add over all these products. Yeah? So now let's find the sum. So now I have hn minus k here. I'll demarcate it here like this. I have xk here. And I shall evaluate. See, now it's very clear that for n less than 0, this sequence does not overlap the sequence at all. And therefore, yn is equal to 0 for n less than 0. Subsequently, what happens? Afterwards, how many points overlap? You see, when n reaches 0 and moves beyond, which are the points that overlap? The point from k equal to 0 to k equal to n. So, for n greater than equal to 0, the sequence yn takes the value summation k going from 0 to n, half raised to the power of k, multiplied by 1, of course, because these are all 1s. So this would take the value, well, one can evaluate this, it's a geometric progression. So we have 1 minus half raised to the power of n plus 1 divided by 1 minus half. So this gives us a complete expression for the sequence yn. In this case, it is convenient to calculate yn analytically. In fact, we are using a combination of graphic and analytic approaches in this case, because we have graphically obtained the regions and the limits of summation and analytically obtained the expression in some zones of n. let's take another example where it is convenient to calculate the convolution entirely graphically. This particularly happens when we have finite length sequences. By finite length sequences, I mean sequences which have a finite number of non-zero points, particularly if they have non-zero points all clustered around some value. In that case, it is, of course, when a sequence has a finite number of non-zero points, we say it is compactly supported on the independent variable axis, as we did for the continuous case. But in addition, if they are clustered, which is often also the case, around some region. So, suppose all the non-zero points are between 0 and 5, right? It is convenient to calculate the convolution graphically. So, let's take an example. So, we have the sequence xn described by 0 everywhere else except for the following points. At 0, 1, 2 and 3, it takes the values respectively. Now, what I will do is here, although some of the values are negative, I shall still write all the dots or all the sticks on the upper side. So, one must not miss, because you see in general those values could be complex and then we do not have to keep on drawing a plane. So, it will be easier just to draw sticks here and represent the value in future. So, we have just 4 non-zero values given by 3, minus 2, 1 and minus 1. So, these are the values of the sequence at the points 0, 1, 2 and 3. We should also consider a sequence Hn given by the values 1, minus 1 and 1. At the points 0, 1 and 2. And we wish to convolve these sequences. So, of course, now here comes the guideline. Which one do we fix and which one do we shift? Now, the general guideline, even in the context of discrete time systems, is that we prefer to fix the sequence that is longer and shift around or move around the sequence that is shorter. So, we will take the same example here. See, although in this, maybe what I will do is to make the sequence a little more, long. Let us have this sequence with one more value. Let this take the value 1 at this point 4 and 0 everywhere else, right? So, now clearly this sequence is longer and this sequence is shorter. So, it is convenient to move around h and fix x. So, what we will do is we will write x of k. And we will straight away construct h of n minus k. Now, I will do it right here. So, you see the 0th point would go to, so it is very clear. You see the 0th point would go to n. At n minus 1, you shall have the 1th point which will come here. So, now I keep erasing points one by one as I take care of them. The 2th point comes to n minus 2. So, this gives me h of n minus k. As a function of k. Now, for each n, we need to evaluate the output. And of course, we can see what the range of the output will be, meaning what ranges, what values of n will have non-zero outputs, can have non-zero outputs. Well, clearly, the non-zero outputs would start when this clashes with this, which means when this, the so-called the engine of the train, reaches the last bogie of the static train, right? So, when n becomes equal to 0. And the last non-zero point shall occur when the last bogie of this train touches the engine of that one, right? So to speak, so when n minus 2 reaches 4, right? So what is the range of non-zero values? From n equal to 0 to n equal to 6. Alright, let's calculate the non-zero values. So I'll calculate a few of them. I don't think we need to illustrate by calculating all of them. So we'll calculate a few of them. So let me do it here. Let me calculate a few of them. Okay. Now let's calculate y of 0. What would y of 0 be? There will be only one clash, so 3 into 1, that's 3. So y of 0 is 3. What about y of 1? Y of 1 will have this clashing with this and this clashing with this. So minus 2 into 1 plus 3 into minus 1, that makes minus 5. Alright, so minus 5. At 2, this would clash with this would clash with this, and this with this. So you have 3 into 1, 3, plus minus 2 into minus 1, that's 2. 3 plus 2, 5, plus 1 into 1, that's 1, so 6. So at 2, the output is 6. And this can be continued up to the point 6. So one can keep calculating the outputs. I don't think I need to illustrate it beyond that. I think it's clear. I hope it is. If it is not, please ask me. Right? Now the calculation is clear. What we need to emphasize are some points in regard to the range of non-zero values. In general, suppose we have a finite length pair of sequences. So suppose we have the sequence xn supported. Now I use this word support for n between n1 and n2. That means xn is non-zero only in this range. Now I must emphasize that when I say xn is supported between n1 and n2, I don't mean that xn must be non-zero for all those points. What is certain is that xn is 0 outside that range. But it could very well happen that one of the points in the interior are also 0. That's perfectly acceptable. The support is the region which completely encompasses the non-zero points. Right? So it could happen that some point inside is also 0. Yeah, is there? Okay, so now let Hn be supported from n3 to n4. Then we ask, what is the support of the convolution, right? What is the support of the convolution? Well, it is very easy to see that the convolution is supported in the region where k lies between n1 and n2. I mean, see, we wish that these two must happen simultaneously. I mean, you know, it must, for the output to be non-zero, there must simultaneously be a non-zero value on x and a non-zero value on h. And therefore, you must have k between these ranges and n minus k between these. And if we simply add, addition is a valid operation on two inequalities, right? So when we add the inequalities, we shall have n between n1 plus n3 and n2 plus n4. So the support of the output is between n1 plus n3 and n2 plus n4. So, as a particular example, we look at the previous case that we discussed. The previous two sequences had respective supports from 0 to 4 and 0 to 2, and therefore the output was supported from 0 plus 0, that's 0, to 4 plus 2, that's 6. And what about lengths? You see, suppose the number of points between n1 and n2, including n1 and n2, is, let's say, m, and the number of points in Hn is L. Then the number of points here is m plus L minus 1. So, to take an example, in the previous case, m was equal to 5 and L was equal to 3, and the number of non-zero points was 5 plus 3 minus 1, that's 7, right? So, this can be extended. Now, you see, the idea of shapes or the idea of patterns is there in sequences. But sequences are always discrete. I mean, they are always, they're very well defined entities as opposed to continuous time or space functions. At every point, at every discrete value of the independent variable, you have a well defined value, real or complex. So, in many ways, sequences are easier to deal with than functions. Although we start our understanding or our analysis of systems with continuous time or continuous functions, actually it turns out that sequences are far easier to handle mathematically, as you can see from various examples. Further, we have also drawn a sufficient number of parallels now between the continuous case and the discrete case. Now what we need to do is to complete this drawing of parallels by looking at a few more issues in the context of discrete time. For example, what we had earlier reasoned out was that I could find out the output of any linear shift invariant discrete time system by convolving the input and the impulse response. That means the impulse response characterizes a discrete time LSI system completely. The impulse response, it must be remembered, is also a sequence like any other sequence. Yeah? The first important parallel that we need to draw is, for practical reasons again, is it all right or is it possible to obtain the impulse response from the step response, right? So, in other words, can we express the unit step in terms of the unit impulse, or vice versa, the unit impulse in terms of the unit step? Well, not surprisingly, the answer is yes. Not only that, it is far easier to do it in the context of discrete time systems. So, it turns out that if we look at the sequence un, then u of n minus u of n minus 1 is delta n. So, it is a very, very neat expression. One may like to draw a parallel between this and the idea of differentiation. Recall that in the context of continuous variables, the derivative of the unit step gave us the unit impulse. But here, the first difference, this is called the first difference. The first difference operated on the unit step gives us the unit impulse. I am sure this is not at all difficult to visualize. You see, u of n is 1 for n greater than or equal to 0. U of n minus 1 is 1 for n greater than or equal to 1. So, when we subtract this, all the ones for n equal to 1 and beyond are cut off. leaving only the one at n equal to 0. So it's a very neat operation. You see, I mean, there's so much more neatness in the context of discrete time systems. Maybe that is the reason why in today's world, with the availability of digital devices and digital signal processors, there is a greater and greater emphasis on doing signal processing or signal analysis or system construction or system realization with digital or discrete time means. Now, there are advantages and disadvantages. We will see them as we proceed. But one of the advantages that we can see is that discrete time systems are neater to handle. They are easier to analyze in some ways. I must also mention, to be fair, a disadvantage. See, discrete time systems don't really handle the gamut of system behavior. That is the problem. So we'll see later that although there are so many good things about discrete time systems, they don't really capture system behavior completely. If one tries to model or if one tries to realize a continuous variable system with an appropriate equivalent discrete variable system, the difficulty comes in being faithful to the behavior of the original system. Yeah? Anyway, coming back to this discussion, then un minus 1 gives us delta n. So, in fact, we can now use the suppose we knew the output to un. So, suppose the unit step sequence, when applied to the discrete system, gave us what we call the step response, unit step response. Which we shall denote by S of n. S of n is the unit step response of the system. Then, by using the property of shift invariance, u of n minus 1 would result in S of n minus 1. This is LSI, this is linear and shift invariant. So, u of n minus 1 would result in S of n minus 1. Yeah? And this is from shift invariance. And of course, then from linearity, by combining additivity and homogeneity, you would have u of n minus u of n minus 1 would result in S of n minus S of n minus 1. And therefore, we can obtain the impulse response. I might write it here. The impulse response of the system is given by S of n minus S of n minus 1. So, if I know the unit step response, the unit impulse response can be obtained by taking the first difference on the unit step response. This is called the first difference, an analogous word to derivative. It's called the first difference in the forward direction. Well, actually forward, it's called the first difference in the backward direction because you are choosing the point before. Now, backward differences are causal. Causal means they involve values that have already been obtained. A forward difference would be Sn minus Sn plus 1. Now, forward difference anticipates values. You are bringing in a value from the future. So, it is not very commonly used. So, normally we make use of a backward difference like this, right? So, the backward first difference, that's the most technically correct expression. Now, you see, for a continuous function, it matters little whether you take xt minus delta or xt plus delta minus xt or xt plus delta by 2 minus xt minus delta by 2 and take the limits as delta tends to 0 in the derivative. So whether you take a forward derivative or the left-sided derivative or the right-sided derivative or the central derivative, it matters little if the derivative is continuous. But this is a difference in the context of discrete variable systems. There is a difference between forward difference, backward difference, and one can also have something called a central difference. But for a central difference, you need to move half step beyond the current point, which is not practical. So there is no simple way of obtaining a central difference. But one can have a forward and a backward difference. And the forward and backward difference need not be the same. That's because one way to think of it is that discrete functions or discrete signals or sequences are inherently discontinuous. I mean, there's nothing continuous about them. So we don't have to bring in everything from continuous, signal cases to the discrete case, right? There are some fundamental differences that would remain because you're inherently dealing with discrete entities which are in that sense discontinuous. They're not defined at points in between. So one needs to take care of these little differences. Now, today we take up one more issue in the context. You see, we've been talking about differences. And now we brought out most of the similarities between the continuous time case and the discrete time case. We've also brought out some differences. All along in the course, even beyond this, we shall take these two streams in parallel. So we shall keep building up notions that are relevant to the continuous time case and then bring them over to the discrete time case, so to speak, and then compare and contrast. We shall continue this pattern in the course in future. But now, at this point in time, we need to make a detour again, not a detour really, again a movement back to continuous time based on our experience in discrete time. See, the question relates to derivatives. We have been hinting at this question for a while. We've been saying, well, a derivative operation or a differentiator is a linear shift invariant system. We've also shown earlier that a running integrator is a linear shift invariant system. And we found out explicitly the expression for the impulse response of a running integrator. Now the question is, what is the impulse response of a differentiator? We have been hinting at this question for a while, and now I think we need to answer it before we proceed to any other subject. I shall only begin by looking at the impulse response of an identity system first. Right? So, you see, it's very clear. What would a differentiator do? I mean, what do you mean by the impulse response of a differentiator? The impulse response of a differentiator would be obtained by applying, in principle, the impulse to the differentiator and querying the output. Now, we don't at the moment know what the derivative of an impulse is. That's what we need to build up. In fact, I think it will be a while before we can, really understand this. So we should devote a significant part of a lecture to this discussion, and therefore we shall proceed from this point onwards in the next lecture.